Hello, this is another video on the video series on current electricity. In this video, we are going to look at factors affecting the resistance of a conductor. As we've done in previous video, that a material has resistance, which is if it has a kind of opposition to the free flow of current through it. So if it makes it difficult for current to flow through it. Now this resistance is affected by some factors. So that's what we are going to go through. The first we are going to look at will be the nature of the conductor. So if depending on the material of the conductor, then the resistance will be different. Resistance of a wire depends on the nature of the material. Is made of. For example, copper has a higher resistance than silver. So what that means is that silver is a better conductor. So it's easier for current to flow through silver than copper. So although silver is more expensive, that's why you hardly see silver in electrical wire. But silver is a better conductor, a better electrical conductor than copper. Another factor is the length of the wire. Length of the wire. Resistance of the wire is directly proportional to length. That is a longer wire, I'm going to do it this way, as the length increases, the resistance increases. So which means the wire of length 10 meters, we have a higher resistance than the wire of length 5 meters, for example. So if I write it mathematically, I can write that R proportional to L. Okay. So another factor is the cross-sectional area. Cross-sectional area. The resistance of a conductor or a wire is inversely proportional to its cross-sectional area. Cross-sectional area. That is, the thicker the wire, the thicker the wire, the lower its resistance. Okay? So R is inversely proportional to the cross-sectional area. Okay? Another factor is the temperature of the wire. So the temperature of the wire will also affect its resistance. The higher the temperature, of a conductor, the higher its resistance. The higher its resistance. So there's a relationship that is used to determine this. So if I have a wire at a particular temperature, if the resistance at the temperature θ1 is R1 at θ1 and R2 is the resistance at θ2, then the resistance at θ2 can be calculated using the formula. Alpha, change in temperature. So change in temperature is basically θ2 minus θ1. 1 plus alpha equal to so that's the formula you can use to determine the resistance, where alpha is the temperature resistance coefficient. Okay. So those are the factors. Now, if you look at the previous factors, we've established that the resistance is directly proportional to the length and is inversely proportional to the area, cross-sectional area. So if I combine those, I can write that R is proportional to L and inversely proportional to A. So if I remove this sign of proportionality, I can introduce a constant there. R will be, so the constant will be, is rho, which is known as resistivity of the material. As that before, the cross multiply here, you have RA equals rho L. So it means rho will be RA over L. So rho is the resistivity of the material. So what do you think the unit will be? Resistance is in ohms. Area is in meters squared, and length is in meters. So one M will cancel one M here. So the unit of resistivity will be 1 meter. Okay. So this is the formula for calculating the resistivity of the conductor. Now the inverse of resistivity is called conductivity. So conductivity, this is the reciprocal of resistivity. We've done this before in previous video. It measures the heat with which a material allows current to flow through. So if I recall the mathematical relationship for resistivity, I can write for conductivity sigma equals 1 over rho. So if I substitute the equation for rho, I will have 1 over RA over L. So if I rearrange this, I will have L over RA. So it means sigma equals L over RA. So that's the formula for calculating resistivity. Resistivity is sigma, is denoted as sigma, and it's measured, and the unit will be the inverse of basically. So inverse of ohm, inverse of meter. So that will be the unit of conductivity. Okay, so let's look at the example. In example 1, we have to calculate the resistance of a 100 meters copper wire of cross-sectional area 2.5 millimeters squared at 20 degrees Celsius if the resistivity of copper at this temperature is 1.72 times 10 to the minus 8 meter. So what do? Let's list what we have. We have we have to calculate the resistance. That's what we are looking for. And we have the length as 100 meters. And we have the cross-sectional area as 2.5 millimeters squared. So here there's a mismatch of units. We have to make sure that there's consistency in the unit. This is meters, this is millimeters. We have to make sure we convert this to meters squared. So how do we convert that? How many millimeters will give you 1 meter? So that's basically times 10 to the power minus 3. And so meter. That's what you want to do. 1 mm is 10 to the power minus 3 meters. So that means you divide by 1,000 here. So because there's a square here, there's an area, so you have to square the conversion factor. So that will give you 10 to the power minus 6 meters squared. So that means the area will be 2.5 times 10 to the power minus 6 meters squared. Okay? So that means we've divided by 1,000 times 1,000. It gives an area. Now we have the area, then we have the resistivity rho as 1.72 times 10 to the power minus 8 meter. And you have to calculate the resistance. So if you recall the formula for resistivity, rho is Ra over L. So if I make R the subject, I'll have R as rho L over A. So if I substitute what I have, R will be rho is 1.72 times 10 to the power minus 8 times L 100 divided by A, that is 2.5 times 10 to the power minus 8. So if you punch your calculator, even I can see, 10 to the power minus 6. Okay. Now, if you punch your calculator, I want to leave this first. This 10 to the power minus 8 and 10 to the power minus 6. If I do 1.72 times 100, 172 divided by 2.5, so that gives 68.8. So R is 68.8 times 10 raised to the power minus 8, but we have 10 to the power minus 6 here. So we apply law of indices, this one goes up. We have 68.8 times 10 to the power minus 8 minus 6. So that would be 68.8 times 10 to the power minus 8 plus 6. That's 68.6 times 10 to the power minus 2. So if I write it, if I remove this, I can write it as 0.686. So that's the solution to that. Resistance is 0.686. Okay. Then another example. The resistance of a uniform copper wire 50.0 meters long and 1.15 millimeters in diameter is 0.830 ohms at 20 degrees Celsius. So what is the resistivity of the copper at this temperature? So here you want to find resistivity. You have the length as 50 meters. We have, this time we have diameter 1.15 mm. And if you convert that to meters, that would be 1.15 times 10 to the power minus 3 meters. Okay. So you have to make sure that the unit is the same. Then the resistance is 0.830. So you have to find the resistivity here. Now you record the formula for resistivity is Ra over L. So let's substitute what we have. Rho will be R. But now we don't have A, we have diameter. So let's first calculate the area, the cross-sectional area. So because the wire is like this, and the wire we have a circular cross-section. So these are the cross-section looks like. If you are holding a wire and you look at the cross-section, you see a circle. So you have the diameter of the circle, which is 1.15 mm. So the area is basically the area of the circle, pi d squared over 4. So pi r squared, but r, r is p over 2. So if I replace that, then I will have d squared over 4. And that will give you 22 over 7 times d, that's 1.15 times 6 power minus 3 squared, then over 4. Come to my calculator, I will have 22 over 7 multiplied by times squared. So that gives an area will be 1.039 times square it because you have to square it and square it minus 6 log in 6 2 times 3. Okay, so that is the then meter squared now. That's the area. Now I can use the formula for resistivity now. Rho is RA over L, and that will be 0.830 multiplied by 1.039 and times by minus 6 and divided by the length 50. Okay, so if you multiply that out, you have 0.83. So the resistivity is 1.72 times 10 to the power minus 10 meters. Okay, so that is the solution. I hope it makes sense. If you don't have the area and you have the diameter or the radius, you calculate the area using pi r squared, the area of the area of the circle, or you use pi d squared over 4. So let's look at another example. Example 3. At 20 degrees Celsius, 33 meters of copper wire has a resistance of 0.639 ohms. So what is the resistance of 165 meters? So here you just have the length and the resistance at a particular condition, and you have to find the resistance that corresponds to another length. Now this is a little bit tricky, but if you understand the problem, you understand the concept, you should be able to solve this. It's easy. Now let's recall the relationship between resistance and length. R is proportional to length, you remember? So the longer the wire, the higher the resistance. Now to remove this sign of proportionality, I can introduce the constant. Let's say this time around, K is like duration. R is KL, so it means that K is R over L. So R over L is a constant, which means if I have for case 1, I have R over L. For another case, I have R over L. So R over L for the first case must be equal to R over L for the second case. So R1 over L1 must be equal to R2 over L2, basically. So now I know, for the first case, I know L1 is 33 meters from the question, and the resistance that corresponds to that, R1, is 0.639 ohms. Then I have another length, R2, L2 as 165 meters. I'm to calculate the resistance that corresponds to that. So by applying this equation, this relationship, then I will have R2 to be by cross multiplying here, R1, L2 divided by L1. And that will give me R1 0.639 times L2 165 divided by L1 33. So L2 will be 0.639 multiplied by 165 divided by 2.2. Ultimately 3.1 5 ohms. So you can see that because we have longer wire now, we have higher resistance value. Okay, you can see that the higher the longer the wire, the higher the resistance. Makes sense. So that's the resistance value. Then the last example. So you have to compute the resistance of the hardened copper rod, 2 meters long and 8 millimeters in diameter, if the conductivity of the material is 5.7 times 10 raised to the power 7 per ohm per meter. So that's the unit. Now here you have the length as 2 meters, you have the diameter as 8 millimeters. So if you change that to meters, that will be 8 times 10 raised to the power minus 3 meters. Then you have the conductivity, sigma, as 5.7 times 10 raised to the power 7 per ohm per meter. So you have to find the resistance. As you recall the formula for conductivity, conductivity is L over Ra. It's the inverse of resistivity, because resistivity is Ra over L. So if I make R the subject of the formula, then I'll have R to be equal to L over sigma A. So, but I need to determine the area because I don't have the area. So area is pi d squared over 4, over 4. And that will be 2 over 7 times b, that's 8 times 10 raised to the power minus 3 squared divided by 4. Okay, so if I multiply that out, I'll have 8 squared over 50, that's 50 times 50.29 times 10 raised to the power minus 6 meters squared. So that's the area I got. So if I substitute that here, R will be the length, 2, divided by the conductivity, 5.7 times 10 raised to the power minus 10 times 10 raised to the power 7, and multiplied by the cross-sectional area, 50.29 times 10 raised to the power minus 6. Okay, if I multiply it out, then I'll have 5.7. I have 6.98 times 10 raised to the power 12 minus 4. That's minus 20. 7 minus 20. Okay, yeah, minus 4. So very low resistance. So that's the resistance then. Okay. So because you have very small wire, so the state resistance is small. Okay, 2 meters. Okay, so that's it for the video, and I'll see you in the next video. Bye bye.